Page 27, Exponential Regression. Data. The data at the right shows the cooling temperatures of a freshly brewed cup of coffee after it is poured from the brewing pot into a serving cup. The brewing pot temperature is approximately 180 degrees Fahrenheit. So we have our table of values, time in minutes, and temperature in Fahrenheit. Go ahead and pause the video, write down these calculator notes. These are the steps on how to do this in the TI Inspire. Okay, so now we're going to do an exponential regression. Part A says to determine an exponential regression, model the equation to represent this data. So to do this first, I'll show you the Desmos.com way. So we go to Desmos.com, go to Start Graphing. If you have your table of values already on the computer in a spreadsheet sort of way, you could just copy them and paste them in. If not, you'll put the plus sign and go to Add Table, and you would type in each one separately. From here, we have all of our points in the scatter plot. Notice it's a negative correlation right here. So to get exponential regression, we're going to press Y1 and then the similar button. A times B caret X1. So that's your exponential regression. To get your R, we're going to click this thing called log mode. So from here, we can find that our A is about 171.5 and our B is 0.99. So we could go ahead and write that on our notes. Okay, part B. Compare and contrast the R for exponential, linear, and quadratic. Which is the best fit for the data? So our R for the exponential is negative 0.985. In addition to our correlation coefficients, let's also calculate our determination coefficients. Okay, let's find the linear regression, the quadratic regression. So to do that, we just press Y1, similar to M times X1 plus B. So that's our linear. Let's go ahead and record our mx plus b in here. And our R is negative 0.9695. And our determination coefficient is 0.9399. And let's do the quadratic regression. So we have y1 similar to a times x1 caret 2 to the second power plus b times x1 plus c. And notice there's not a correlation coefficient, there's just a determination coefficient. Okay, so the best fit for the data would be exponential. Now, why would that be? I mean, the R is bigger on this one. It's closer to 1. If this wasn't attached to real life meaning, it would be quadratic. But since we know that the temperature's not going to, for some reason, go down and then go back up after the time goes on, it would be more reasonable to make it exponential. So the reason would be the R is close to 1 and the temperature is not going to go back up. So C, based on this equation, what is the initial temperature of the coffee? So it's going to be this equation right here. We have F of T equals, and since it's the initial, our T will actually be at 0 minutes. If you remember, anything to the 0 power is 1. So 1 times 171.5 would be 171.5. So 171.5 degrees Fahrenheit would be your initial temperature here. Now D, it says, when is the coffee at a temperature of 106 degrees? Basically, when F of T equals 106, what does T equal? Well, let's go to Desmos and see that. So we're looking at the exponential graph, so we can go ahead and hide the other two. And it says when F of T equals 106, so let's just put Y equals 106. So let's see when those cross. It looks like they cross at about 41. So about 41 minutes. And E, what is the predicted temperature of the coffee after 1 hour? Well, it's measured in minutes, and there's 60 minutes an hour. So let's go ahead and plug that into Desmos. Let's say X equals 60. Okay, let's see when that intersects. It's at about 84. 84.4. So we can write that 84.4 degrees Fahrenheit. And that's how you do this. This is how you do regressions on Desmos.